So another application of derivatives, we've seen kinematics. Now we're going to look at rates of change, because that's what a derivative is. It is a rate of change. And so if we have a function, like this first example that says this is how many bacteria there are in a colony after T hours. If we take the derivative of that, we find the number of bacteria per hour. Because what we're doing is basically, if this equation, n is your number of bacteria, t is your time, your derivative is dn dt. That is your change of bacteria over your change of time. And so by finding the derivative and plugging in 10, we're finding out that after 10 hours, it's increasing at 75 bacteria per hour. At that moment, that's the instantaneous rate of change at that moment. So looking at this, if we look at a derivative and we find out we've got a critical value at 2.5, we set up our number line using that negative 2.5. Well, if you plug in something less than negative 2.5, this function's decreasing. After negative 2.5, it's increasing. But in the context of this equation, we're only thinking about time greater than or equal to 0. And so the first derivative is always positive when time is greater than or equal to 0. That means that our bacteria are always increasing. So whereas this model probably works over a specific amount of time, this is sometimes a limitation of a model. You can't always have bacteria increase forever. They're going to run out of food, and then you get a problem with your graph. But according to the model, it does show that it's always increasing. So would I say this is realistic? No. You're going to have problems. So a model works for a while, and then sometimes chaos theory comes into play, because things go crazy for a bit until they stabilize again, and then they can follow the model again. So we see this with populations all over the place. Populations increasing exponentially, then runs into food shortage or problem, and then boom, it goes back. I love this example. You can imagine this controlled laboratory somewhere in Winnipeg, just having mosquitoes. And the population is increasing by that exponential function. They have volunteers that just stick their arms into the lab so that the mosquitoes can increase. I'm sure that's what's happening. T is measured in days. We want to find the growth rate. So we want to find out how many mosquitoes per day are being produced after 5 days. So anytime you're looking for that growth rate, it's going to be a derivative. We have a chain rule here when we take the derivative, because you've got a function inside of E. So the derivative of E stays the same, but then you multiply by 0.09 because of the chain rule. If you plug in 5, you get roughly 35.3. Now, you can't have 0.3 of a mosquito, so we could say that the growth rate is approximately 35 mosquitoes per day at that moment. And that's a rate of change. That'd be nice. So, got your chain rule for your derivative. Plug it in. So always your rate of change, you need to include your units. So you look at, well, what was the temperature in? It was in Celsius. What was time in? Time was in minutes. So after 10 minutes, it's cooling at negative 2.44 degrees per minute. Nope. Okay. And the last one. I can put it back, but I'll put up the answers for the last one right now so it's on the video, and then you can go and check the last one later. So you can pause the video at the end, but oh, now you want to quickly take a picture so my views don't go up too high. I understand. And here's the last one that you were wondering about before.